Hello, everybody. Hello, welcome. It's great to see you all. Thank you for joining today. My name is Neill Renton. I'm a chemical engineer. I'm a principal consultant and also the UK country manager for ORS Consulting. And it's great to be here with you today and get the chance to talk about a topic that I get involved in quite a lot, which is the application of process safety times and SIF response times. These are two different things, and I hope today to be able to share some information with you, share a bit of learning, a little bit of my experience on these topics. And I'm going to look forward to working with you over the next 50 minutes or so. I've got a few slides. I don't try to bombard people with information in these type of sessions. So I've got something like 10 slides. It's mostly pictures. There's only a tiny little bit of text. So mostly we'll be having a look at things. And yeah, there'll be a chance to quite a lot of time to ask some questions. Now, could you everyone do me a favour? You know what it's like. We've all been working on Teams for the last few years. It can be quite difficult when you're sitting in the room yourself to know if everyone is there. Is everyone really listening? Would you go ahead and maybe just type in if you can hear me okay and your everything's working fine for you? Would you just say hi in the Q&A or something like that? Like just type in hi or give a thumbs up or something like that, and just let me know that the Q&A part of it's working okay. So type anything you want. Just say hi, Neil. How you doing? Something like that in the Q&A. It should come up for me. There's one. There's a few. Very good. Yes. And yeah. Thanks, man. Great. Perfect. You've come up with that. I do see that. So yeah. Thank you. That's great. Anyway, at least it's working. So feel free at any time, during the talk, feel free to just go ahead. If you want to ask a question, go ahead and stick it in that Q&A part. Nazar is online here. He'll be helping me with he'll be helping me with publishing the questions. And yeah, we should have a good sort of 20 minutes, 25 minutes after the presentation for you to ask questions, and I will try. Hi, thanks guys. That's all great. Perfect. Perfect. Thanks so much. Good. Well, I hope you enjoy it. Let me just let me switch over to the slides. Nazar, I think you need to do that. So if you can switch over to the slides for me. Hopefully, you can see the slides now. Yeah, so can you see the slides okay? Let me know that. Nazar, can you see the slides okay? Yeah. Oh, do it by yourself. Okay, fine. Look, here we go. I will now share this screen. Hopefully you can see that. Let me know you can see that, okay? Yep, perfect. Good. So, like I say, I'm going to cover the difference between process safety time and SIF response time. And what I'm going to do is, here we go, bear with me, thanks. So why should we even study this topic? This is a photograph of the aftermath of the Texas City explosion that happened at BP's refinery in the noughties. And what you're looking at there is just the aftermath of the explosion. So this unit, the isomerization unit, basically created petrol. So it was sort of polishing up the components that go into petrol for cars. And the heart of the unit is these two huge distillation columns, which are helping to improve the quality of the petrol. And it's a well understood process. This had been in service for many decades. There's a unit like this in most refineries creating the petrol. but they lost control of this system during a startup event. And finally, they had a loss of containment from this tall pencil, this big black pencil here. This was a knockout drum. They had a loss of containment from the top of this. And that created a big flammable gas cloud, which ignited. And unfortunately, there were a lot of people located here in temporary buildings. And sadly, 15 people lost their lives and dozens of people were injured. And I mean, these things like this, when they happen, unfortunately, I've had to investigate a number of incidents like this. They're very complicated. There's lots and lots of different things happen, very often years before the actual event itself. But at least part of the problem here was there was an issue with the instrumentation, the protective instrumentation that supports those columns. And this is just a schematic representation of one of those distillation columns. You know, this distillation column's basically got vapor, hot vapor coming, being created here in this reboiler. So we get vapor going into the column, and it heads up through the distillation column as a vapor. We've got liquid coming down the column. Sorry, here it's coming here. And there's a condenser here that's condensing some liquid, and the pump's pumping it in. So we've got liquid falling down the column. And to try and manage the liquid level, we've got a level transmitter here. That's that little LT. And that's trying to tell the operator where the liquid level is sitting. And to try and help with that, there was a high level alarm and a low level alarm on a different device. This was impaired, this wasn't working. And so the operator didn't know where the level was in the column. This was also not working very well, and they were changing it out prior to the startup, prior to the event happening. And the sort of impairments with these devices, at least in part, meant that the operator did not know where the liquid level was. And so when something else happened during startup, the liquid began to build, and eventually the liquid went right over the top. These relief valves opened, and the liquids were routed to the tall pencil, the big black pencil, and that's where the loss of containment happened. I got this diagram from the investigation report, and there's also a link there to the CSB site. There's a video, there's the investigation report. There's like a lot of extra information there that you could have a read up of. I always encourage everybody to have a look at sort of previous events to try and understand them. So these sort of instrumented systems, and you can see there's a few of them in this plant, and I'm sure in your plants that you're involved with, there's lots of these safety instrumented functions, as they're called. It's protective devices that are trying to stop like this liquid overflow. They're trying to stop overpressure. They're trying to stop low temperature event by detecting it with a transmitter, and then a logic solver trying to get something to take action. So like the pump being switched off, or an isolation valve being closed, or something like that. And the question we're very often interested in is, how quickly does this equipment need to work? How fast does it need to work? It's obviously no good if the liquid can build in the column over, 20 minutes. It's obviously no good if the fastest that this can all operate is 45 minutes. It'll operate after the hazardous events occurred. So it's an important question, this. It's like, how fast must this equipment respond? And for any of you who sort of work with older equipment that was designed, some time ago, and you're responsible for operating it, this is actually quite a difficult question to answer, because we certainly know how fast the valve closes. We might know how fast the transmitter reacts. So we know a bit about how quickly the kit can react. But the real question is, how quickly should it react? Can it act fast enough to prevent the hazardous event that it's trying to stop? Because very often, around most of the plant, those events maybe haven't happened before. and we can't know for sure, is this kit good enough? Will it actually help us in a real event? So that's what I'm going to concentrate on. And you can look at almost any major incident on a complex process plan, and there will have been an instrumentation issue involved somehow. So let's dive straight in. What is the process safety time? It's defined in international standard IEC 61511, and it's defined like this in red. It's the period of time between a failure occurring in the system, and that failure has to have the potential to give rise to a hazardous situation, and the occurrence of the hazardous event if the SIF is not performed. Now, as usual with standard, the English that's used in standards, it can read a little bit like gobbledygook when you first read it. So I'm going to show an example, and let's see if we can just get a common sense definition of that. It's basically the time between an initial failure happening, like a valve failing closed, and the vessel filling up and the liquid overspilling into the next process downstream from the vessel. Or it would be a valve failing closed, and that would be the failure, and then the pressure building inside the vessel, and eventually the pressure reaching the design pressure. So it's a duration of time between something going wrong in the process and then the design limit being reached. It's as simple as that. The PST, it's a property of the process, and it's determined by the volume, mass, and energy balance. So it's got nothing to do with instrumentation. It's only a function of how much stuff is going into the vessel or equipment, how big the vessel is, and what its design limit is. Yeah, and I'm going to show that in a real example in a second. It's a performance measure that instrumented systems have got to meet. So obviously we have to, the instrumented, the protective system, so the level trip or the pressure trip or the temperature trip, it has to be able to detect the failure and take executive action, close the valve or switch something off before the design envelope is reached. So it's in some way, it's some kind of target that the SIF has got to meet. And again, just for emphasis, in case you're new to the subject, the SIF's made up of a transmitter, a logic solver, and an end element. And let's have a look at a real example to see that. So hopefully you can, I just took a snip from a P&ID there. This is a vessel. It has an inlet here with fluids coming in, a pressure, a temperature, a flow rate, and a composition. It's got vapor going out the top, and it's got two liquid outlets. It's got a liquid outlet here with a level control valve on it, and another liquid outlet here that's heading off somewhere else. It doesn't matter where it's going. Here's an example of our safety instrumented function. Here's the level logic solver represented on the P&ID. This is the transmitter. So here's the level transmitters. There's three of them. 1, 2, 3. There's also a couple other level devices here, but anyway, let's concentrate on these. So we've got 3 level transmitters. They're all feeding forward into this logic solver, which is the computer basically running the control system. And then the computer will then tell a valve upstream of the vessel to close if in fact we get high level in the vessel. Because, you know, obviously something's gone wrong when this level valve might have failed, or this valve might have failed closed. We've blocked the liquid outlet. Liquid starts to build, and it builds at the rate it's coming in at. This is what I mean by the fact that the process safety times are a function just to the geometry of the equipment and the flow rates and the temperatures and compositions. It's got nothing to do with instruments. It's like once you shut the valve, how big's the vessel, how much stuff's coming in, and that'll determine how quickly it fills up to the top and eventually carries over. You know, liquid carry over downstream of a vessel, we can't know what's going to happen there. There might be a compressor downstream. There might be some other process that's sensitive to liquid going into it. Once we fill this vessel up, that's it. We're assuming that the design limit's been breached and we're going to get a hazardous event. So process safety time, it's quite a simple concept to understand in the first instance. It's just how long does it take from this valve failing closed to, for a level example, the vessel filling up completely and then liquid being sent downstream. That's the design breached once we've done that. We could define another event in this vessel on pressure. We could get a valve failing on the vapour outlet. Pressure would start to build. It would build and build, and then this, a different SIF, this pressure SIF, would then detect that increase in pressure, tell the computer, oh, watch out, we've gone above the set point for high pressure, and then the computer would then again try to shut a valve upstream of the vessel to isolate it from the pressure source to try and prevent the pressure building any further. Obviously, if this didn't operate, pressure would just keep building, and eventually we would rupture the vessel unless the PSV operated, but another safeguard. So I hope that gets over the basic concept. The process safety time, it's a property of the process, got nothing to do with the device itself. The difference between the process safety time and the SIF response time. So this second concept of a SIF response time, what is that? Well, let me just break. I just got a very simple graph together to sort of let you see the difference between the two concepts. So here we're showing pressure inside the vessel, and we get some kind of failure, a blocked outlet on the vapour side of the vessel, and pressure starts to build. So the blue line is showing how pressure is building inside the vessel. And the rate that builds at depends on the size of the vessel, the amount of vapour space, and the flow rate into the vessel. And if it keeps going, and nothing does anything, it just keeps going, eventually we go past the design pressure of the vessel, and we define that as the hazardous event. We're taking no credit for the PSV there. Pressure would just build until the vessel ruptured. So let's have a look and see a few different time intervals of interest. Well, first up, here, this is the design, this is the final design limit. This is the initial failure happening. So as per the definition of process safety time, it's from the moment the initial failure happens all the way along to the design limit being breached. So that is the process safety time, that whole distance between the initial failure and the design limit. That's the process safety time. But a few other things are interesting on the way. Pressure starts to build, and in this point, maybe even a good operator in a control room might notice that pressure was building. So this is what's called the early response time, and the operator might indeed notice this, although most times, well, sometimes yes. I don't know if you've ever been in a control room. I've been in lots. It's a complicated business managing an entire plant, and they're having to keep an eye on lots of different things. But sure enough, they might see something, but most likely not, until this happens, till the alarm enunciates. So usually there's a high pressure alarm that comes in before the trip, and that's to try and tell the operator, watch out, something's happened here, you better be careful there. And so that's important, the alarm. But again, we're relying on a person noticing something. He might, or she might, or they might not, and pressure will continue to build. As the pressure keeps going up, at some point it reaches the trip set point. So it reaches the set point of the safety instrumented function. And at that point, we could start the clock, if you like. As soon as the trip set point's reached, the instrument then has this length of time between the trip set point being activated and the design pressure being breached. And that's how long the actual SIF's got to react. So it's only going to start doing something the moment the set point's reached. And the transmitter then has got to see that the pressure has reached the set point. It's got a flip back one. So the pressure transmitter here has got this, the pressure builds right up just before the trip set point. And as soon as the trip set point's reached, that transmitter has got to be working at that point. And then it's got to send its signal into the ESD system, into the logic solver, which has got to take the signal and go, oh, that's compare the value of the transmitter against its set point value, realize that the two are the same or it's gone above it. And then the computer's got to process that and go, okay, right, you better shut the valve, send a signal to the valve, and the valve's got to close. So there's quite a lot to happen between this pressure being reached and the valve actually being told to close and then actually close. The valve itself's got to close. And that's going to take a few seconds, depending on the size of the valve and the type of the valve. So that's why we say that this length of time between the set point and the design limit being reached, that's why we say this is the SIF response time. It's a target that the instrument has to meet. So when at the start of the presentation, when I said that, we're interested in how fast these devices have to work in order to prevent an event. For an existing plant, this is really the thing we're interested in, the SIF response time. You can see it's much shorter than the process safety time. The process safety time is more commonly used during design when none of these set points are fixed and we're trying to decide where should the set point be. So this tends to get used a bit more during the design process when we're trying to confirm what the set point should be. But once it's installed and it's in operation, yeah, this then becomes the thing of interest. How quickly must it react? Because obviously we want to know it can do that. So two different concepts: process safety time, the time between the initial failure, the valve feeling closed, and the design limit being breached, and SIF response time. That's how quickly does any protective system have to operate to prevent the design limit from being breached. It's a much shorter time than the process safety time, and it's a target that the equipment has to meet. I hope that's clear. I'm just having a look in the Q&A there and hoping that you've so SIF response time is less than, yeah, someone just said there, so SIF response time less than the PST, absolutely, absolutely. Process safety time will always be bigger than the SIF response time. And remember that the SIF response time, that's a target, it's a performance measure that the device has to meet. The actual SIF response time, in other words, it's test results, the SIF test time, that's got to be less than the SIF response time because it mustn't allow the design limit to be breached. So there's a wee bit to think about there, and a bit of care is needed. Anyway, I hope that's all clear and helps. Now, how do we do this in practice? What does a real, what does a real thing look like? Let me just go here and flip forward one. So sometimes when it's complicated, we've got to build something like this in a process simulation software. Sometimes we've got hand calculations, because like working out how quickly pressure builds in a vessel once the valves close, working out how quickly level builds once the valve closes. Okay, you can do this in a fairly straightforward hand calculation. And if you make some conservative assumptions about the CV of the valves and the upstream pressure and the downstream pressure, you can make some simple conservative assumptions and just do it quickly by hand. Sometimes it's a bit more complicated and we need a dynamic model in the process simulation software. This is just an example of one. I'm sure you've all seen something like this before. I think the important thing is you don't no way do you need to do this every time. I would say maybe 10%, 10 to 15% of the time we need a dynamic model. Most of the time we can get a conservative estimate of both the process safety time and the target SIF response time from a hand calc. But it might need something like this. And once we've got our model, whether it's hand calc based or whether it's a simulation based approach to it, then we can start to have a look. So here's some output from a real. So this I've taken. Thanks to Dario for thanks to Dario. Oh yeah. Thanks to Dario, my colleague Dario Potsa, for doing this for me. This is some output from some real studies that we've been doing recently, and it's looking at pressure build-up following a valve failure. And this grey line showing what happens when the valve starts to fail. So this is the valve position. So you can see that valve opening. So this is the vapor outlet valve failing closed, failing closed, failing closed, eventually closed. It's 0 here. And you can see what happens to the pressure upstream. Nothing happens. Even when the valve starts to close, nothing happens to the pressure upstream. Nothing happens to the pressure upstream. Just starts to kick up, and then really starts to kick up, once we get down to almost, it really doesn't start to build properly until the valve's completely shut. And then pressure starts to build in the system, build, because we've obviously got stuff coming forward still. Keeps going up, keeps going up. At some point, reaches the trip set point, just here at 28 seconds. Keeps going, keeps going, keeps going. And it would just keep going past the design pressure unless our SIF takes action. So, yeah, this is the design pressure shown in this dotted line here. This is the SIF trip set point. So you can see we're interested at 28 seconds, the SIF trip set point's reached. And then just 2 and a bit seconds later, the design pressure's reached. Now, that's fast. We best hope we got some nice equipment there that can react within 2 and a bit seconds. So that's the process safety time. It goes from the moment the valve starts to fail all the way until we reach the design limit. So that's the process safety time. SIF response time, that target required SIF, is much shorter. It's the time between the set point and the design limit being breached. Hope so that's clear. And this is the thing we want to test against. You can see right away just from common sense, there's no point in testing against this. I mean, that's going from 20 seconds to nearly 30 and a half seconds. Once the trip set point's reached, if we add on 30 seconds there, we get away over here somewhere up at 58. We're going to go miles past the design pressure. In fact, it's going to fail. So the process safety time's not much helped us in an existing system. It's helpful when we haven't put the set points together yet and we're trying to design the thing, then it's helpful. But once it's in and working, yeah, this is the thing we're interested in. Can it meet this? Given because this blue line is only determined by the flow rates and the volume going into the closed system. It's purely a property of the process. And so this is the target that the SIF's got to meet. Hope so. This is a good question. Well, we're going to come on to the second example. It gets a bit more complicated. This is one of my last slides before I give a summary. This again, just a real example, and this was quite a bit more complicated because we were measuring the pressure transmitter. Was quite a bit away from the system that we were interested in, and so obviously the pressure is not the same everywhere. I mean, if the pressure transmitter's in the vessel and we're interested in the vessel, it's straightforward. If the pressure transmitter's 100 meters downstream, there's obviously going to be a big difference in the pressure between the location where the transmitter is and the actual and maybe the pressure elsewhere in the system upstream of that. And that was the case here. the trip set point was reached at the transmitter, but it was the pressure at the green point we were interested in, and that when the second location in the system reached the design pressure, that's what we were worried about. So you can see the same thing again. The blue line's the valve closing. We can measure the PST from the moment the failure starts up to the design limit on the green system. And the SIF response time, we needed to define that using these two lines. Once it reached the trip set point on the orange, where the transmitter was, that the clock started. And once the pressure built in the second part of the system, when the green line reached the design pressure. So that was just a wee bit more complicated and needed a bit more thought, but same concept, same idea. SIF response time, the time between the trip set point and the design limit. So in summary, before we go on to answering the questions, have a think. While I'm going over this summary, you have a think if you've got any questions or you want to ask me something. Point one, just from that picture from the explosion in Texas City, safety instrumented functions, so pressure trips, level trips, temperature trips, they need to work fast enough to try and prevent a loss of containment or other hazardous event once there's a process upset. Process upsets are going to happen all the time in plants, and we need these devices to operate quickly enough that they stop something bad from happening. Point two, the process safety time is the time between the process upset happening, so the valve failing, and the design limit being reached. It is a property only of the process, the volume of the system, and the mass and energy balances. It's got nothing to do with the devices. The SIF response time is the time between the SIF trip set point being reached and the design limit being broken. And it's a performance target that the SIF must achieve. So we need, this is in effect, this is a target saying, this is how fast you need to work, buddy, like do your job. And that's what we should be testing against. And at point four, yeah, that testing needs to show that the system can indeed get do its job. The transmitter, the logic solver, and the end element all need to work together faster than the SIF response time target. And that test result then can be recorded, compared against the SIF response time target, and we can say, yep, all good, it's doing it fast enough. Well, that's it in terms of everything. That's the technical content, if you like. That's all I wanted to cover. I hope I've just given these simple ideas a bit of life for you. And I can see the questions. I'm going to just start answering a few questions. Let me just I've got to work out how to, I'm going to publish. So I can publish a few things here. Publish, yeah, that's all good. Why is there such a long delay for the pressure build? Yeah, that's okay. This is a good question. Thanks. There's loads of good questions here. I'm going to try and get through as many as I can, and we've got a little bit of time. So, first question from just a simple, and I'm very conscious today. There's people from all over the world joined the call today, and some of you are very new to this subject. So no questions a daft question. Just ask anything you want, and also there'll be some people on the call who know quite a lot about it. Thanks for your patience. There's obviously people new to the subject, and it's important that they get some insight into it. So one person asked, is the SIF response time less than the process safety time? I hope you can see from the graphs, yes it is. If I go back over here, yeah, it's definitely SIF response time shorter than the process safety time. Somebody's asking, what's the difference between the SIF and the SIL? Well, SIF stands for the safety instrumented function, and if I flick back, let me flick back a couple, flick. Yeah, the safety instrumented function is this equipment here. So it's the transmitter, level transmitters, the logic solver, which is the computer controlling the ESD, the emergency system, but it's a computer on the plant. And that computer then talks to what's called the end elements. There's an example end element there. a shutdown valve, the computer would then tell that valve to close. So a safety instrumented function is made up of 3 elements: transmitters, a computer, and an end element, a valve or a pump or something that can take some action. Those 3 things together form the SIF. The SIL, on the other hand, safety integrity level, that is a reliability measure that's trying to tell you how reliable that equipment needs to be in order to work safely. Because of course, sometimes these things can break, they don't work, you know, the wiring might be affected, the transmitter might be able to blink. And the SIL is a target reliability that it needs to meet given the type of consequence it's trying to prevent. So if we're trying to prevent a loss of containment that we could get multiple fatalities at, we'd obviously want this to be very reliable. It might have a very high SIL rating, a SIL 3 requirement, say, and that corresponds to reliability. A very high reliable system like 0.0001 or something like that, failures, 1 failure in 10,000 or 100,000 or something like that, just as an example. So I hope that answers that question. Let me keep going. Can we say, someone's asking, can we say that the PST is approximately 1.5 to 2 times the SIF response time? This is a great question, comes up a lot, and there's a lot of confusion about this. Let me go to a good slide for that, so we can answer that. To someplace here, let me show it. Yeah, there we go. Right. So this is something that comes up a lot. Should the target SIF response time be half the process safety time? And in fact, not just the target SIF response time, but the actual SIF response time. So how quickly it really does respond. That's a different idea again. And I would say that's a bit approximately right in practice. The sort of 1.5 to 2 times. That's approximately right, and it is a rule of thumb that people use in the design community when they don't have any set points for the system set, but they do know this. They know that if the failure occurs, when is the design limit breached? So they know the process safety time, and it's a general rule of thumb to say, well, just half it. And with half of it, let's put the set point where it's roughly 50% of the process safety time. But it's a rule of thumb, and it's to help you try and set safe set points for the SIF, so that it operates roughly twice as fast as it needs to. But you can see here, like, you can see even in this example, yeah, it's like, for sure we should be focusing on this. Whatever this really is, the target, that is what we should be concentrating on trying to work out. And we should be testing against that. I think, unfortunately, this sometimes gets called the process safety time. Some people refer to this time as the process safety time, the time between the set point and the design limit being reached. It's not correct as per the standard. The standard says the process safety time is this, but we're obviously just very interested in that. So that was a good question. Let me go and have a look at a few more. Hang on. I need to bring my cursor back this way. So let's try and few. And thanks for your questions. I hope, and thanks for taking the time to ask the questions. I'm going to try and get through as many as I can. Let me have a look and see now. There's a few new ones in here. Okay, why is there such a long delay from the pressure build up? Yeah, so someone's asking, that's a good question. Like, the valve's starting to close there. Why does the pressure not build when the valve starts to close? Well, that's just down to the hydraulics. And as long as there's a space for the valve, as long as there's some cross-sectional area, the flow is going to continue. We've got pressure upstream of the valve, we've got pressure downstream of the valve, and all that's going to happen is the velocity, obviously the velocity is going to change, but the pressure gradient across the valve doesn't. Downstream pressure is not really changing, the upstream pressure is not really changing, But as the valve starts to shut, cross-section area gets smaller and smaller. So I could show you the flow rate, the actual velocity through the valve is getting faster as it closes, but the pressure upstream of the valve does not. It's only once we just start getting down into this low part here, we've got very little of the valve left, a tiny hole left. That's the point at where the pressure has to start to build, and we can't get rid of it anymore. So yeah, that's why that happens. Next one, someone's asking, someone's asking, oh, hang on, I'll try and publish this. One. Somebody's asking, some people have asked a sort of similar few questions. Is there any standard or guide that, well, I'll go back to these other two first, right? Would you say the process safety times defined in the design phase for selection of alarm and trip set points or selection of operational parameters such as flow, heating, or maybe both? Great question. Yes, it's much more useful at design stage. We don't have any set points in place yet, might not have the alarm set point or the trip set point in place, but we know the blue line. We know how the blue line is going to happen, and we know the process safety time. So we can try to make sensible decisions about the alarm set points to make sure we're within the process safety time first. And then obviously we can stretch this red line back a bit, we can tighten it up a bit. Obviously, if we tighten it up, it gives the process more flexibility to operate without trips. If we make the trip set point too close to the operating pressure, obviously, as it keeps going that way, we're going to start getting spurious trips, or at least we're going to get a lot of upsets and stoppages that aren't going to help us. But if we make it too close to the design limit, then, well, the valve might not have enough time to close. So process safety time, good rule of thumb, just half it for the SIF response time, give a reasonable window. But it's not the end of the story. I would say that is a rule of thumb and not a design approach. With regards to calculated SIF response time based on the PSD, how is this used in the SRS? Often response time requirement is stated per component, initiator, logic, solver, and end element. Is the calculated SIF response time included in the SRS directly, and the required response time per component is added based on the overall SIF response time? Again, that's another great question. That the SRS is such an important document for both the design stage and then through life for the equipment as it's operated. It's the overall SIF response time that's important. Those individual component, so the transmitter, what the person's really asking there is like, is it built bottom up or is it built top down? And the answer is it's built top down. It's the SIF response time target overall. That is the overall performance requirement needed. And then we can look within that and say, right, in order to meet that, transmitter, you can have 1 to 2 seconds, logic solver, you can have, for the computer to work, half to 1 to 2 seconds, and the valve, you can have a second per inch, and all of that has to combine, and it has to be less than the required or target SIF response time. There's quite a lot of mix-up. My experience of trying to use this in practice is there's quite a bit of confusion between the target SIF response time, which needs to be in the SRS, and it needs to be stated clearly how quickly the overall device has to work. So there's quite a bit of confusion between the target and then the actual SIF response time. I mean, that's the quality of the transmitter, the logic solver, and the valve, the size of the line, how quickly the valve can close, etc. Those things are, that's all to do with the equipment. This target SIF response time, this has actually been determined by how quickly the pressure builds. This is also a property of the process this time, just like the PST is. It's a fraction of the PST, and it's only been determined by the gradient of this line, where the trip set point is and where the design pressure is. Those are the three things that are determining how the gap, the time in there. It's something the SIF has to achieve. So I hope that answers that. A lot of great questions. Let me keep going. A few other questions. Is there any, say, standard or guide? Hang on, I'll publish the next couple. Standard or guide. Is it necessary to kind of rate of change when calculating process safety time? Okay, that's good. Should the SIF response time be determined before the LOPA? Where is this normally included? Okay, also more good questions. Let's have a look. Right, first one. Is there any standard or guide? Oh yeah, that's a good question. Actually, I see there's a lot of good questions there. I'll maybe just answer one of them, Bashri, so I'll give a chance for somebody else to ask a question. That rate of change when calculating the process safety time. Well, I hope you can see there that the rate of change, like that's sometimes a performance measure, a different performance measure that's used for instrumented systems, because this is very fast. And so instead of the executive action working where the trip sets point's reached, and then as soon as that point's reached, the instrument, then the transmitter picks it up, the logic solver gets it, and then it's just based on a straight value. But there's a different way of asking the valve to close, and that's basically to look at the gradient of the blue line. And that gradient's the rate of change that's been talked about in the question there. And if we can measure the gradient, if the gradient goes above, if it becomes too steep, even before it reaches the absolute trip set point, if the gradient's too steep, in a way it's like a warning that's about to it's going to say you're not, there's a problem here. This gradient's so steep. If we wait till the trip set point's reached, we're not going to be able to meet the SIF response time. So it's a second way, like a second layer of protection, if I can call it that. Although it's just the computer. It's actually something happening in the logic solver. The transmitter, the logic solver, and the valve are the same. It's just the computer doing something fancy with a gradient in the line as a second trip, if you like. There's the absolute trip, and then the rate of change. We just measure the gradient and say, "Oops, we've got a problem here." So it's about the functionality of that. So thanks, Bashri. That was a good question, and I'll if it's all right, I'll try and pick it up somebody else who's asked a question. Should the SIF response time be too low? Yeah. Very high CV. Yeah. Should the SIF be determined before LOPA? I will publish that. Yeah, publish that. Thank you. Let me go and just dive into those. Yeah, is it because the very high CV of the ESD SV? Yes, I think that refers to the question back about why is it taking so long for the pressure to build. The answer to that is yes. Someone else asking, for a small process safety time or SIF response time, what further protection layers exist? Well, that rate of change was one, and that's in the logic solver, so that's one example of it. The other layers that can exist, let me go back and let me just flip back on a couple of slides. Yeah, so obviously the alarm and the operator response, that is a layer of protection, but not always a very reliable one, especially if it's in a stressful situation. But it can also be quite good. My experience, and it very much depends on the person, the operator, and how complex the plant is. So yeah, just depends. You could have a second device, and you might finally, there's beyond the device working, beyond the instrument device working, we might have another layer like a PSV or something else like that. Someone just asking, last couple of minutes before we're out of time. Yeah, should the SIF response time be determined before LOPA? Where is it normally included, the results of those calculations? Calculation reports or LOPA reports? That is a good question, a very good question. I would like to see it calculated before LOPA more often than it is, because I think, especially for existing devices, and I mean, even during the design process, it would be better to have it before the LOPA, because at least you could tell whether or not it was realistic that an instrumented function could provide protection in that circumstance. You know, if the SIF response times, like that example that I showed, like 2 and a bit seconds, like is it? Can we really say are we going to get a SIF that can react that quickly? Maybe, but maybe not, and maybe LOPA is not appropriate then because of that. So I think I would like to see it before the LOPA. The reality is it's not very well aligned. That's the reality. Can happen after quite a lot. Go into the SRS afterwards. It's not in the LOPA team don't always have that information. It'd be better if they did have that information. So that's my given. A couple of last new ones. NORSOC defines ESD response time. Is that analogous for the SIF response time? That's a good question, Jean-Carlos. That ESD response time in NORSOC is it's not quite the same. We're out of time as well. I will see if I can get a response to you on that. Just look me up on LinkedIn and we can DM me and we can talk about that a bit more, because we've reached the limit of the time today. So I'm going to stop presenting that. I'm going to go back to sharing my camera. Hang on a second. I don't know. Nazar, if you can maybe just let me, if you could just present me, if you know what I mean. And yeah, I'll just say thanks so much, everybody. That's our 50 minutes up. I'm so glad you were able to join. I hope that's given you some insight into the topic. Feel free to get in touch. You'll get me on LinkedIn, or just type my name into Google. You'll also get my contact details that way as well. Good luck in whatever you're doing. And